Okay, well, yes, we're going to deal with the difficult area of geology, probably one of the sort of big areas of conflict when we think about origins issues. And particularly we're going to think about evidence for the flood. Now, I wanted to start with this book. This is a book written by two biblical scholars, Tremper Longman and John Walton. It's called The Lost World of the Flood. It was published back in 2018, and I read this book recently. And one of the things you need to know about these two authors is that neither of them is a biblical creationist, right? So they're both theistic evolutionists of one kind or another. And yet, in this book, they basically agree with young age creationists like me that the Bible plainly describes a worldwide flood. They explicitly say in their book that they disagree with evangelicals. This is a very popular view among evangelicals, that you can interpret the flood account as simply a local flood or some sort of regional flood in the ancient Near East. They disagree with this view. They say that doesn't do justice to the biblical text. The Bible plainly describes a worldwide flood. However, neither of these men believes that the flood was in fact worldwide. They believe that the flood was local. And they argue that the Bible is describing a local flood as a worldwide event simply for rhetorical effect. Okay, the Bible author is using hyperbole to describe the flood. This is the position they take. Now, why do they come to this quite sort of strange, counterintuitive conclusion? Well, one of the reasons, and they say this over and over again in the book, and in fact they kind of rope in an old Earth geologist to write a chapter in the book to this effect. They argue that the reason we know that this is the case is because there's no geological evidence of a worldwide flood. Right, so the flood must have been a local event that's being described as a worldwide flood simply for theological effect. So what I want to do in this talk is just address this claim head on. Is it correct to say that there is no geological evidence of a worldwide flood? And I want to sort of tackle this question under three headings. I want to give... What's the cable there? Oh.
Sorry.
So I want to sort of tackle this question. Hopefully that's going to come back on the screen.
No?
Yeah.
Oh, great. So I want to sort of tackle the evidence for worldwide flood under these three headings. First, what's it doing now? Very strange. Hopefully it's... There we go. Firstly, I want to look at widespread catastrophically deposited sedimentary rock strata. Secondly, I want to look at large-scale soft sediment deformation features. And then thirdly, I want to look at extensive high-elevation, low-relief erosional surfaces. Now, don't worry about the details at this point. I'm going to explain all of these as we go through. And I want to argue that these three things together make a very compelling case for a worldwide flood that had worldwide geological effects. So I want to begin with the first of these, widespread catastrophically deposited sedimentary strata. I want to give a couple of examples. We could look at numerous examples, but I have time just to give you two. The first one is the Shinarump Conglomerate, which is a remarkable sheet-like deposit. It's sheet-like because it's quite thin. It's only about 15 to 30 metres thick, but it's extremely extensive. And it crops out across northern Arizona and southern Utah and parts of neighbouring states in the southwestern USA. It originally is thought to have covered more than 365,000 square kilometres, so it's extremely extensive. And when we look at this rock unit, we find that it's basically made up of large pebbles and cobbles of quartz, quartzite, and chert. We also find fossil wood. We find petrified wood, fragments, sometimes even very large logs within the Shinarump Conglomerate. We know that the quartz pebbles have been transported some considerable distance because they don't match any nearby source. So they've come from a long way away. And we also know from the cross bedding, which is a kind of inclined bedding that forms when sediment is transported as dunes, that it was deposited by very fast-flowing currents of water. So it's really quite an extraordinary, extensive rock unit. The question is, how was it formed? The conventional idea is that the Shinarump Conglomerate was basically deposited by normal braided streams that over time deposited conglomerate in such a way that the conglomerate deposited by the streams coalesced to form this extensive blanket of conglomerate. So you have to imagine individual sort of smaller streams that eventually, their deposits coalesce to form this blanket of sediment. Now, there are several problems with this idea. One of the issues is that there's no evidence in most of the Shinarump Conglomerate outcrop for the kinds of erosional channels that you'd expect from a braided stream network. So in most places where you find the Shinarump Conglomerate, it sits on top of the underlying rocks with a very flat contact. So we don't see evidence of, river or stream channels. You do find some in some places, but very, very, very few. Mostly it just has this flat contact. The other problem is that there is absolutely no example anywhere in the modern world of a thin conglomerate of uniform thickness being deposited over such a broad area. I mean, it's just completely unheard of. We have no modern analogues for this kind of rock unit at all. So it's no surprise that back in 1938, the geologist Gregory said that the conditions under which the Shinarump was deposited are difficult to visualise. Right? He's right. It's difficult to imagine a modern environment that could give you something like the Shinarump Conglomerate. However, if you think about the features of the Shinarump, its broad sheet-like geometry, the fact that it's uniform over thousands of square kilometres, the evidence that the clasts, the cobbles within the unit have been transported long distances by powerful water currents, that's exactly the kind of rock unit that you might imagine being deposited by an event like the worldwide flood. So that's one example. Let's look at another example, the St. Peter Sandstone. So the St. Peter Sandstone is, again, a very extensive sandstone unit that we find in the mid-continent of the United States. It's a very pure quartz sandstone. It's made of quite well-rounded, well-sorted quartz sand grains. Again, it's relatively thin. It's about 25 to 30 metres thick. But it's enormously extensive. You can trace it from Minnesota in the north to Arkansas in the south, from Illinois in the east to Nebraska in the west. So it's a huge blanket of sand. Covers about 650,000 square kilometres, mostly in the subsurface, but that's kind of the aerial extent of this rock unit. Now, when you look at it in outcrop, it's typically massive and homogeneous in appearance. It's quite difficult to see structure in it. But in some places, like southern Wisconsin, there are outcrops where you have these enormous crossbeds. These are 11-metre thick crossbeds that, again, show that parts of this formation were deposited as extremely large sand dunes. Now, the conventional idea about the St. Peter Sandstone is that it was basically deposited in an ancient shallow marine setting, an offshore shallow marine sand. But again, we face the problem that when we look for similar examples in the modern world of shallow marine sands that are this extensive, we don't find them. And in fact, there are other differences. So, I've already said that the St. Peter is relatively thin. It's 25 to 30 metres thick, but that's much thicker than, say, the sands on the present-day Atlantic Ocean shelf, which, average about 1.5 to, 4.5 metres thick. And that's before they've been buried and compacted, right? So the St. Peter Sandstone is much thicker than those. But again, when you think about the remarkable purity of this sandstone, its extensive nature, its geographical extent, the fact that it's located in the middle of the continent, right? It's not in the ocean, it's on the continent of North America. All of that fits with what we'd expect from a global flood. So we've got these remarkable rock units, but so far we've been thinking about individual rock units. And I want to go a bit further, because in the 1960s, geologists, mostly working in oil and gas, began to recognize that sedimentary rock strata were actually grouped in packages called sequences. These packages of sediments are bounded at the top and the bottom by erosional surfaces called unconformities. So we have these thick packages or sequences of sediment. And on the right you can see a typical sequence. So we have sandstone at the bottom, and then that's followed by shale and then by limestone. And what I want you to notice about that is that the grain size decreases as you go up through the sequence. So the sandstone is the coarsest sediment, the shale is less coarse, and the limestone is less coarse still. So it's what we call a fining upwards sequence. The grain size fines upwards. And recognizing these sequences has led to the recognition of some incredible global patterns. In 1963, a geologist called Lawrence Sloss identified 6 of these megasequences across the North American continent. So to orient yourself in this diagram, on the left-hand side here we have the standard geological column, where the oldest rocks are at the bottom and the youngest at the top. The black areas that you can see in the diagram, and that's a transect, if you like, across sort of west to east transect across North America, with the mid-continent somewhere near the middle. And the black areas are basically gaps in the geological record, which are unrepresented by sediments. So they represent those erosional gaps, those unconformities. And then the yellow and sort of brownish areas, that's where you've got sediments deposited. And you can see that there are these 6 packages bounded by these erosion surfaces, the black sort of gaps, stacked up one on top of another, and they're given these various names that you can see in the white typeface. So this was a very sort of significant discovery, because what we realise is that you have these massive packages of sediment that can be traced right across the North American continent. Let's look at one example of one of these sequences, the Sauk sequence, the lowermost sequence. You can see it exposed in Grand Canyon. So we have here at the base, we have the Tapete Sandstone, then it's followed by the Bright Angel Shale, and then followed by the Muave Limestone at the top. So here's our classic fining upwards sequence, okay, coarser sediments fining gradually upwards. Now what's remarkable about this is that you can not only trace these units all across North America, but you can actually then trace the same patterns on other continents, okay? So in 2018, a creation geologist called Tim Clary published a paper in which he compiled more than 1,500 geological columns from 3 continents. So he'd looked at North America, South and Central America, and Africa. And he used these geological columns to construct maps showing the distribution of prominent rock units. And what you can see here is his map across North America of the Sauk sequence, the sequence we just looked at in Grand Canyon. The yellow unit is the sandstone, so that's effectively the Tapete Sandstone. Now it's called the Tapetes in the Grand Canyon, it's given other local names elsewhere where you find it, but they're basically all the same sandstone. It's one sort of massive blanket of sandstone that essentially covers North America. And as I mentioned a moment ago, you can then trace the same patterns on other continents. So here on the left, we've got a geological column. This is the Grand Canyon, where we have this crystalline basement with an erosion surface. And then we've got the Sauk sequence, and here's the basal Sauk sandstone, the Tapete Sandstone. But go 2,000 kilometres to the east, and here in Wisconsin, we've got the Mount Simon Sandstone, again resting on an eroded crystalline basement. It's effectively the same sandstone, right, 2,000 kilometres away. But then, head even further away to Libya in North Africa, and we have effectively the same sandstone at the same level in the geological column. And then in Timna, in southern Israel, again you can see the same Sauk sandstone and resting on a eroded crystalline basement, just like it does in Grand Canyon. So these are global patterns. Now, what would we expect if there had been a global worldwide flood? Global patterns demand global causes, right? And we have an explanation in the creation model for these global signatures that we see in the rock record. So we have these widespread catastrophically deposited sedimentary strata, but we also have large-scale soft sediment deformation features. And again, we could look at a number of examples, but I want to look at one in particular, the sandstone pipes in Kodachrome Basin State Park in Utah. Now, Kodachrome Basin State Park is about 8 square kilometres in area. It's somewhere to the east of Bryce Canyon, which you may have heard of. The rocks in the park are mostly flat-lying sedimentary strata of Jurassic age. You can see the local geological column here. The Jurassic rocks belong to the Carmel Formation, the Entrada sandstone, and then the Henryville sandstone. And there are also some younger rocks, in particular some conglomerates that are Pliocene to Pleistocene age. So the Jurassic sediments are sort of 150, 160 million years old. The conglomerates are probably somewhere around sort of 5 million years old in conventional time. But one of the most remarkable features of Kodachrome Park are these vertical sandstone columns or pipes that cut through the surrounding rocks. And because of weathering and erosion, some of them stand out as these sort of towers or spires. The tallest one, I think, is about 52 metres high. They can be sort of 15 metres across, so they're big features. And in 1985, geologist Dwight Hornbacher mapped about 67 of these pipes around the park. So how did these pipes form? Well, we know that the sand in the pipes came from the sedimentary rocks below, okay, because sometimes you can actually find fragments in the pipes of material that was brought up when the sand was injected, and you can match it to rocks below. So this is Chimney Rock, and there's my colleague Ray Strom next to Chimney Rock, and you can see that massive sort of mudstone fragment which came from 100 metres below. Okay, and was brought up when the sand was injected. How was the sand injected? Well, Hornbacher looked at a number of different possibilities, but he came to the conclusion that probably a very large earthquake was the likely source of the injection of the sand. A massive earthquake. Earthquakes can fluidize and remobilize sand and cause it to be injected into the surrounding rocks. But here's the point. Of course, if you're going to inject sand in that way, the sand has to be soft and unconsolidated, right? Has to be soft and unconsolidated at the time the injection event happens. And here's where we run into a problem for the conventional timescale. We know that the sand was sourced from these parts of the Carmel Formation. We know this is where the sand came from. We know that the pipes intrude this member of the Entrada sandstone, the Gunsight Butte member, and in fact at least one we know intrudes the Escalante member. So the sand has come from here right the way through those rocks. But there's a time difference in the conventional model between these rocks that are the source beds and the rocks that are intruded. And the geologists, some geologists have concluded that the injection event probably happened around the time the Henryville sandstone was deposited, and so they say there's at least a 10 million year time gap between the deposition of the sediments and the time when they're injected. Now that's problematic enough. You know, how do you keep the sand unconsolidated under conditions of deep burial for 10 million years? But actually the problem is probably greater than that. Because Hornbacher found that there was at least one pipe in the park that was capped by one of those conglomerates, which is meant to be very young geologically. It's meant to be about less than 5 million years old. And there were even fluid escape structures that went from the sandstone pipe up into the conglomerate, which implied that the conglomerates must have been there at the time that the sand was injected. Now, if that's the case, if Hornbacher's right about that, the time difference between the time the sand is deposited and the time it's injected is not 10 million years, it's 150 million years. All right. Now, how on earth do you keep the sand from being lithified under conditions of deep burial for 150 million years? We know that the area where these pipes are now found was buried more than 1,200 metres deep. And rocks buried that deeply in the presence of mineral-bearing waters readily get lithified. So how did the sand stay soft? However, the flood model helps us to explain this, right? Because in the flood model, the time difference between the time the sands are deposited and the time the injection event happens is not 150 million years. It might just be weeks or months. So we don't have the same time conundrum within the flood model. So again, the worldwide flood described in the Bible, if it deposited these sediments, helps us to explain these data in a way that the conventional model can't really explain them. One final piece of evidence that I want us to think about. So we've thought about widespread catastrophically deposited sedimentary strata. We've thought about evidence that the time that it took to deposit those strata was relatively short. One final piece of evidence concerns these erosion surfaces, high elevation, low relief erosion surfaces. Now, to understand the significance of these features, we've got to think about conventional ideas about how landscapes develop. In 1899, the geologist William Davis proposed his famous geomorphic cycle, in which the Earth's landscape is sculpted over vast periods of time by the same kinds of processes we can observe going on around us today. So his model basically begins with an episode of uplift. So we have an episode where the land is uplifted, and you have this youthful, geologically youthful, high elevation, low relief surface. But what happens once you uplift that surface? It becomes exposed to erosion. Okay? Erosion begins to eat into that surface and begins to produce valleys in that surface. And after a few million years of erosion, we have this stage of maturity where we have these deep valleys with narrow divides. Eventually, of course, erosion lowers that plane to sea level. Okay, erosion wears away that plane until you have a low elevation plane, which is the stage of old age. Okay, but it's low elevation, right? It's at sea level. So the point here is that if we find high elevation, low relief surfaces, according to conventional ideas about how landscapes develop, they should be geologically young. Right? They're geologically young features. And so pervasive were these kinds of cyclical models of landscape development that in 1954, William Thornbury, a geomorphologist, basically said there can be no high elevation, low relief surfaces of any great geological age anywhere in the world. Right? They've all, if there are high elevation, low relief surfaces, they've got to be young. Thornbury was wrong. Right? Thornbury was wrong. Because we now know, thanks to the work of a number of geomorphologists over a number of decades, that high elevation, low relief surfaces are not only common across the world's continents, but they're often regarded as of immense antiquity. Really, really old. So one classic example is the so-called Gondwana Surface that was mapped by a geomorphologist, Lester King, back in the 50s. And a lot of other work has been done on it since. It's called the Gondwana Surface because the geological evidence indicates that it was basically eroded before the breakup of the Gondwanan supercontinent in the Jurassic and early Cretaceous. Right? So it's thought to be really old. Right? At least 150 million years old. And yet, it is preserved on multiple continents in the world. Lots of these surfaces have been found in Australia. Twydale and Ollier, two geomorphologists, have mapped and documented many examples in Australia, including the Knot Surface in the southern Gawler Ranges of southern Australia, which was meant to be 70 million years old. Some of them in Australia are even older. The high plains of Kangaroo Island and the Southern Eyre Peninsula and the Mount Lofty Ranges is thought to be late Triassic. That's 230 million years old. These high elevation, low relief plains. And they present some challenges, don't they, for the conventional model. First of all, how did they form? We don't see any surfaces like this being formed by modern erosional processes today. So the first thing is, how did they form? It's hard to imagine slow and gradual processes that could have caused them to develop. But the other problem, of course, is how did they then survive? Having formed them, how do they survive for potentially hundreds of millions of years if erosion has been operating, as we understand it throughout that time? It's no surprise, really, that Twido said this, 1976, there has surely been ample time for these very ancient features to have been eradicated by erosion several times over. But there they are. He says the survival of these landforms is in some degree an embarrassment to all of the commonly accepted models of landscape development. But again, the flood model helps us, doesn't it? Because in the flood model, first of all, we have a mechanism to form these high elevation, low relief surfaces, because during the flood, when the continents are covered with water, and particularly at the end as the waters drain off the continents back into the ocean basins, we have a mechanism for eroding very flat, high elevation erosion surfaces through sheet flood erosion. But we also can explain their survival to the present day because of course, the global flood was only 4,500 years ago and not hundreds of millions of years ago. So the timescale problem is solved within the flood model. We can explain these features, but they're an embarrassment to the conventional model. So basically, to sum up, I think Longman and Walton, in their book, The Lost World of the Flood, are basically wrong. When they say there's no geological evidence of a worldwide flood, I think they're wrong. There is geological evidence consistent with a worldwide flood. We've looked at some of it today, and there's a lot more that we could have looked at if we had more time. And so I think we can reject their sort of counterintuitive conclusion and say that the reason the Bible plainly describes the flood as a worldwide event is because it was a worldwide event, and that there is, in fact, geological evidence to confirm it. Thank you. Thank you.